Welcome to this professional masterclass on healthy buildings. Today, we're setting an elite standard. Our objective is straightforward but absolutely crucial. We are mastering indoor air quality. We're moving way beyond basic compliance and diving right into the absolute cutting edge of building performance science. So let's jump straight into this curriculum and equip you with the insider-level knowledge you need to transform literally any indoor environment into a highly optimized, health-promoting asset. Here's our curriculum progression. We'll start with the foundations of healthy buildings, then move into analyzing pollutants. Next, we'll tackle advanced ventilation, specifically comparing ERVs and HRVs, followed by filtration frameworks, looking at MERV versus HEPA. Finally, we'll wrap up with system maintenance and optimization. Module 1, Foundations of Healthy Buildings, a paradigm shift. Historically, the building industry prioritized energy efficiency over human health. The result? We basically built airtight but toxic boxes. To fix this, we rely on the 9 foundations of a healthy building, a framework developed by a brilliant multidisciplinary team at the Harvard T.H. Chan School of Public Health. Notice just how holistic this is. These core elements apply universally, no matter the building type. We're looking at ventilation, air quality, thermal health, moisture control, dust and pests, safety and security, water quality, noise, and lighting and views. To achieve a truly healthy building, a professional has to systematically address every single one of these vectors. You can't just pick and choose.
Now, I want you to look closely at this number, 950 parts per million. For decades, carbon dioxide was just viewed as a harmless proxy, right? Just a rough indicator of general ventilation. But recent controlled exposure studies, including that research from Harvard, have fundamentally blown that standard out of the water. We now know for a fact that higher-order cognitive function significantly declines at CO2 concentrations as low as 950 ppm. And here's the staggering part. This level is actually incredibly common in indoor spaces. In the past, this would have easily satisfied standard ventilation guidelines. Not anymore.
The crucial takeaway here is captured perfectly in this quote from the underlying research. The evidence mounts for CO2 as a direct pollutant, not just a marker for other pollutants. This realization fundamentally changes the game. It completely rewrites how building professionals have to approach ventilation. You aren't just flushing out body odor or clearing stale air anymore. You are actively diluting a neurotoxin that directly impairs the cognitive performance of the people inside your building. Module 2, Analyzing Indoor Air Pollutants, Defining Threats. To control an environment, you've got to first define the specific microscopic threats that are compromising your air quality. The WellView2 preconditions serve as your professional gold standard for this continuous monitoring. Let's break these parameters down. Particulate matter, PM2.5 and PM10, stems from infiltration and combustion, and it poses a severe cardiovascular and respiratory risk. We measure this with optical or gravimetric sampling. Then we have TVOCs, total volatile organic compounds. These offcasts from building materials and cleaning supplies, causing everything from mild fatigue to actual organ damage. We monitor those using photoionization detectors. We also have to track dangerous combustion byproducts like carbon monoxide and nitrogen dioxide using electrochemical sensors. Plus, we absolutely must account for radon, a radioactive soil gas tested through alpha-track passive sampling. And finally, relative humidity. We track it because it directly drives microbial growth and completely dictates thermal comfort. Mastering these parameters, that's the floor, not the ceiling, of elite building performance.
Module 3, Advanced Ventilation, ERVs versus HRVs.
Because modern buildings are built so incredibly airtight to reduce heat loss, just opening a window, it's no longer a viable energy-efficient strategy. These buildings require an active mechanical respiratory system, like the standard heat recovery ventilation, or HRV, architecture you see right here. This hardware operates continuously. It simultaneously supplies fresh outdoor air while exhausting stale indoor air. But the real genius is the heat exchange core inside that casing. As the two air streams pass each other, without physically mixing, which is key, the system continuously preheats the incoming cold, fresh air using the warmth of the outgoing stale exhaust air. It drastically reduces energy consumption while keeping thermal comfort incredibly high.
But here is where you have to make a critical engineering choice, ERV or HRV. The core difference is that an energy recovery ventilator, an ERV, transfers both heat and moisture between the air streams. This makes ERVs absolutely optimal for hot, humid, and mixed climates, specifically climate zones 1 through 5. They deliver superior long-term value because they automatically manage indoor humidity, preventing really costly moisture damage. Conversely, a heat recovery ventilator, the HRV, transfers heat only. HRVs are strictly for very cold, dry climates, zones 6 through 8, where maximizing heat recovery is the top priority over humidity control. Choose the wrong system for your climate zone, and you will actively create humidity problems that compromise the entire building envelope.
Module 4, Filtration Frameworks, MERV versus HEPA. Okay, so now that we have fresh air entering the building, we have to filter it. And there is a massive misconception in the industry regarding filter efficiency that we are going to debunk right now. To fix it, you have to master CAD, the Clean Air Delivery Rate. CAD is simply the total volume of clean air a system can deliver. You calculate it by taking the filter's efficiency and multiplying it by the airflow rate. This simple equation anchors a totally critical mechanical trade-off in building science. If you use a filter with extremely dense fibers, sure, it catches more particles, but it simultaneously restricts the total volume of air flowing through your system. When you're choosing between HEPA and MERV 13, that KDR equation changes everything. HEPA filters offer extreme filtration efficiency for ultra-fine particles, absolutely. But because they are so incredibly dense, they are highly restrictive to airflow. If you slap a HEPA filter into an average home HVAC system, you will overstrain the blower motor and drastically reduce your total KDR. HEPA is really best reserved for localized, small-volume purification. On the flip side, MERV 13 filters are highly efficient. They capture those ultrafine 0.3 to 1 micron particles like wildfire smoke and viral aerosols, but they maintain sufficient HVAC airflow. Because of this, MERV 13 is actually the superior professional choice for whole-room, rapid-volume air cleaning through central systems. You maximize your total KDR without destroying your mechanical infrastructure. Module 5, System Maintenance and Operational Optimization. You can specify the most advanced mechanical hardware on the planet, but without strict operational protocols, it will rapidly fail. Execution is everything. As professionals, we have to anticipate and troubleshoot these common operational failures. If a system is running but providing little to no fresh air, you're likely dealing with blocked exterior hoods or severely clogged filters. In cold winter conditions, condensation inside the unit can actually freeze, creating a frozen heat exchange core that completely blocks the exhaust stream. If your occupants are complaining of cold drafts, it's almost always a signal of a blocked return stream or, again, a frozen core. And persistent high indoor humidity usually points right to humidistat calibration errors or just insufficient system runtime. Practical implementation means getting your hands dirty. Think about it. You wouldn't drive a luxury sports car for years without changing the oil, right? Yet we literally do this to our buildings all the time. Routine maintenance, like physically cleaning a ventilation grill, is not optional. It is non-negotiable. Physical blockages from dust, debris, and frost will absolutely choke your system. Regular visual inspections and physical cleaning of both interior grills and exterior intake hoods are your frontline defense against mechanical failure. To guarantee long-term performance, we implement this exact 7-step quarterly maintenance protocol mandated by top building science authorities. Step 1, always turn off and unplug the unit first, safety first. Step 2, clean or replace the air filters every 3 months to protect your KDR. Step 3, clear out those outdoor intake and exhaust hoods. Step 4, inspect and flush the condensate drain with warm water to prevent any backups. Step 5, vacuum and gently wash the heat exchange core to remove dust buildup. Step 6, annually check and clean the grills and ductwork. And finally, Step 7, gently clean the fan blades and lubricate older motors if the manual requires it. Sticking to this exact procedure ensures the hardware functions exactly as it was engineered to. We're going to conclude this masterclass with a final provocative thought. Modern science has unequivocally proven that airtight buildings function exactly like living organisms. They rely entirely on their mechanical lungs. So I'll ask you this. Are you actively maintaining your building's respiratory system through proper ventilation, filtration, and operational protocols? Or are you slowly suffocating its occupants with unchecked CO2, VOCs, and particulate matter? Take these frameworks, audit your indoor environments today, and elevate your building performance to the elite professional standard. Thank you for joining this masterclass.